That's what's for lunch. All right. Section 3.3. Here we go. It's all about complex numbers. Mario, tell me a number. And make up any small positive number.
35.
35. Okay. The number 35 is a natural number. Then the set of natural numbers exists right here. Natural numbers, the letter N. That's our counting numbers that we teach our children to learn to count by. Our natural counting numbers. 1, 2, 3, 4, 5, ... all the way up to even 35. The 35 is also a whole number. Set of whole numbers is 0, 1, 2, 3, 4, 5, 6, 7, so on and so forth. Ken, you good?
I just said. It's how it is that. Yeah, what? Yeah.
I just don't want to drink a muscle milk in that class.
Yeah, that's fine.
Thank you. Integers is Mario's number an integer? 35 is an integer. Yeah, it's a positive or negative counting number. Is it a rational number? It is. Rational number being a number you can express as a ratio of integers. 35 over 1, 70 over 2, for example. Rational numbers are also terminating or repeating decimals. So you might see some of those on there, like 2.25, etc. And then is it a real number? Of course, it's a real number. But what we're going to talk about today is that it is also considered a complex number. This is what these are. These are sets of numbers, one contained inside another. Hey, that ship has sailed, my friend. I'll talk to you at some other time.
Can I interrupt?
Yes, I'm recording class. That's make it quick.
Your best knowledge. Okay.
That's my gut. Hurts.
He's already back.
Well, you haven't started talking again, so.
Oh.
Mitch, I love you. You're so fun. All right. Well, okay. So we'll pick on Mitch. All right. Mitch, what grade are you in? Okay, he's the 10th grade. Great. So Mitch is, let's see here. He is a student in this class. He is a member of the 10th grade. He's a member of the student body at Christian Brothers High School, and he's a resident of the state of Tennessee. Okay, so that's a similar example, right? Where like you could kind of describe him with a small group, but then he's also a member of a large group, which is also a member of a large group, which is also a member of a large group. It's kind of like Mario's number 35. My point being, all of the numbers that you've ever experienced in your lives up to this point have actually been complex numbers. Okay, like the number 1, 2, 3, 4, just like they're natural, they're whole, they're integers, they're rationals, they're reals, they are also part of a larger set. It's the largest set of numbers to date. It's called the set of complex numbers. We use the letter C to stand for complex. Okay, D?
So are there a set of numbers that stand outside of this?
To this date, no. Now, I did once upon a time, I was teaching this class, and there was a young man named Adam that was in my class, and Adam was kind of unique. And so he took it upon himself to create a larger set of numbers than that. And he made up some kind of rule by which those numbers were defined. And I was like, good for you, Adam. But, he also created pocket people that were little people that were made out of cardboard that lived in his front pocket. And he would have conversations with them during class. So he was kind of, he's interesting like that. But he said, I'm going to make it my goal to make a bigger set of numbers, Coach Morgan. And I think he called them the Zebarians, the people that lived in his pocket. That was like 15 years ago, though. So I'm going in the Wayback Machine. No, but I did threaten. I used to have ceiling fans in here. I threatened to tie him to the ceiling fan and just turn it on and let it spin for a while if he didn't be quiet. So
for the extras that get extra credit for the bigger sets.
No, he did not. He did not. What'd you say, BJ? I don't know. The ceiling fans are gone. I miss my ceiling fans, though. I did really like them. All right. So once upon a time, mathematicians stumbled upon this equation. They said, gee golly, we wish this equation could have a solution. Now, most recently in this class, you guys have practiced solving these types of equations. This is a what kind of equation, Christian? Quadratic equation. And Nash, how many solutions? 2 solutions. All quadratic equations have 2 solutions per our fundamental theorem of algebra. A degree 2 equation is going to have 2 solutions. Degree 3 would have 3. Degree 4 would have 4, etc. All right, Alfredo, what would you suggest I do to get x by itself? Give me 2 steps.
Just put the one. Think. One.
And then?
Need one.
Very nice. Now, whenever we take the square root of both sides, we want to remember our plus or minus because as Nash told us, there's 2 solutions. So this will be the square root method. And up to this point in your mathy careers, you would have been like, hold up, take the square root of negative. This equation has no real solutions. Okay, and that's true. It has complex solution. And those complex solutions are made of a number, imaginary numbers. And that basic imaginary number is known as I. I equals the square root of -1. Have you all learned a little bit about this before? Y'all went ahead and looked at that delta map. Good for you. Maybe you got freaked out a little bit about it. I don't know.
I got
But-
freaked out by the PF.
It wasn't that.
Integer function.
Oh, yeah.
That
Great.
scared me.
Did you get a chance to ask any questions?
I looked it up.
Oh.
When it said, I didn't know she meant by define it, so I looked at it. But then it was like, so I understand it now, because it's only integers.
Well, and so this is something that you guys might have looked up on your own because I had made that assignment earlier in the week. And what we'll learn about today is that I is our basic imaginary number. It's equal to the square root of -1. BJ?
Doesn't that do?
Well, I'll probably won't check it until Monday when I see you guys again. Because now I'm getting a chance to teach you about it and you'll run off and just, it'll take you 5 or 10 minutes, you'll be done with it. But I is equal to the square root of -1. I is our basic imaginary number. Okay, it's like a lowercase cursive I or italicized I. That's kind of how you would make it look. And then based on that, what we can do is we can consider, let's just look at the first 4 powers of I. Okay, look at the first 4 powers of I. All right, so I to the first power, of course, it's just I. That's just the square root of -1. Real plain and simple. That's our basic definition. There was a mathematician, much like my friend Adam, that time, that they just said, I'm going to create some math and I'm going to make some rules by which this math follows. And so these people did this. They said, all right, well, I squared. Now, if I is a square root, Mr. Green, what happens when I square a square root? Yeah, so the radical sign goes away and we're left with the radicand. We're left with what you were taking the root of. So I squared is -1. Now, friends, that's very important. I squared equals -1. Really helpful fact, because what kind of number is -1? It's a real daggum number and it's an integer. Okay, and so what we're going to notice is that we can make use of the fact that I squared equals -1 a little bit later on in today's lesson. I to the third. Now, if you really get creative, you think I to the third, okay, well, that's cubing a square root, which doesn't really help me much. But if you think about cubing something is multiplying it by itself thrice, and you could sort of cull off one of those and say, well, hey, look, I squared is -1. And so you've got I squared times I, or -1 times I, and that is I to the third. And then last but not least, you got I to the fourth. Now watch my fingers here. You've got I to the fourth. 1, 2, 3, 4. What's I to the second? And what's I to the second? So I to the fourth is -1 times -1, which is 1. And so this pattern of I, -1, -I, 1, then it repeats for the similar reason that you could call off every 4 I's you could pull off. I to the fourth equals 1. And you say, all right, well, I to the fifth is the same thing as I to the first. I to the sixth is the same thing as I to the second. You can take out those 4 I's. So now this pattern, it repeats I, -1, -I, 1. I, -1, -I, 1. And so now we could do as an exercise, say, well, okay, I wonder what I to the 10th power would be. Mitchell Gilmore, what do you think I to the 10th power would be?
That'd be -1.
Very good. And we just follow that pattern, right? We just go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Bing. Now, what's the drawback on doing it that way?
It's gonna take a while.
Yeah, so like if somebody said, what's I to the 273rd power? You know, am I gonna sit there and want to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16? Or should I recognize
So you make an equation to.
multiples of 4? So what we'll do is as an exercise, we're going to take I to the 32nd, I to the 50th, and I to the 7th, and we're going to see if we can break those down into the base, either 1, 2, 3, or 4. All right. And my hint here is just divide by 4 and see if there's a remainder. All right. So like I to the 32nd, now 32 is a multiple of 4, is it not?
Yes.
So we would say this is the same thing as I to the 4th, which is 1.
So. Like, I don't understand all this stuff.
Like the purple and orange and green. I'd like for you to understand it. Let's take a deep dive into part A. And Nash, thank you for having the guts to say, hey, might not necessarily understand that. All right, so I to the 32nd is the same thing as I to the 4th times I to the 4th times I to the 4th times I to the 4th. I'm losing track. Let's see here. 4, 8, 12, 16, 20. I to the 4th, that's 24. I to the 4th, that's 28. I to the 4th, that's 32. All right, there's 8 of them. All right. Now, what is I to the 4th each one of these times? Just the number 1. Right? So we would say this is similar to saying 1 times 1 times 1 times 1 times 1. Mr. Perry, did you need? I do have some tape. You're more than welcome to it. Anytime you want to interrupt, I hope you know that you can.
Certainly. That's not a bother film also.
So that equals 1. Now, similar to what was up in the previous one, what we're doing is we're just saying, well, how could I break down a larger power of I and think about it in terms of either I to the 2nd, which is a nice number, an integer of -1, or I to the 4th, which again is a nice number, an integer. So like we look at something like, let's just do I to the 7th. We'll come back to I to the 50th.
Well, I understand that. I understand that. Very -1.
Okay, so I'll take a different tack then. So like I is the same thing as radical negative 1, and the power of 4 is the power of 4. So this is pretty much just replacing the letter I with square root of -1. And then recognizing that, ooh, if I've got something raised to the 4th power, that's like saying a couple of squareds. And so a couple of squareds, that's nice. And then the squares, square root cancels out, square root cancels out, and leaves you with -1, -1.
Okay, I see.
And then if we get down here, Franklin, you were saying about I to the 50th. You liked that one. So walk me through.
I just did I to the 40, right? Which is, since 40 is a multiple of 4, that would be 1. But then I did 10 after the 10, which we already said. I think it's either I or -1.
Okay.
Could you have done 48 too?
That's what I was gonna say. I like Franklin's idea of he went to the nearest easily like recognizable multiple of 4. Or okay, so Michael says, hey, I like 48 and 2. You know, and the point being, I to any multiple of 4 is equal to 1 and therefore becomes trivial. So it's like, well, that is like just saying times by 1. So what I to the 10th is the same thing as I to the 2nd. And what's I to the 2nd the same thing as? -1. So you see, guys, what I'm doing is look at the hint. It says divide by 4 and consider what the remainder is. Okay. So like if I took 50 and divided it by 4, right? 1, 2, right? So there's a remainder of 2. And so I to the 50th is the same thing as I to the 2nd. So now you can see like some of those larger powers, maybe like Delta Math might give you, 573. Well, just divide 573 by 4, see what the remainder is. And that what you're doing is you're calling out every single I to the 4th, and you're seeing if there's any left over. So like, for example, if this was 33, if this was 33, then I would have what left over, what remainder? I would still have an I right there. And so each one of these I to the fourths becomes trivial because it's 1. And then I'm just left with a nice little I right there. And I could get that by saying, what's 33 divided by 4? And we said that's 8, remainder 1. And there's your 1 right there. Mm-hmm. Mm-hmm. So like I to the 7th, we would say is I to the 4th times Nash. I to the 4th times what? Bingo. And that I to the 4th is trivial. I don't really care about that. And I to the 3rd we know is negative I. Or negative square root of negative 1. Whatever floats your boat. This is uncomfortable. This is weird. This is new. Okay, we're gonna do a lot of this.
So where's the item 7?
Say that again.
Where do we get item 7?
This is just an example.
But I'm saying like where would it come from?
Oh, in application?
Yeah.
Ooh, okay. So
Like would that be like -7?
no. Typically in application, you guys will not you will not encounter large powers of I. And to be honest with you, the I to these large powers is just sort of like, let me get my foot in the door and describe how I sort of works. In application, at least in my experience in math and engineering kinds of classes, you're not encountering rather large powers of I. You just need to know how I to the first and I to the second work, and you'll kind of see that fleshed out in some examples. And what we'll do with these complex numbers is we will operate upon them. We'll do add, subtract, multiply, divide, just like we've done with other types of numbers. Okay. I would expect one of those 4 answers. Highlighted in green. Oh, yeah. We're gonna get there. So like back to this one right here. Like, what did we say? Our answer was x equals plus or minus I. That's where we would say our 2 answers were. So we would say x equals I or x equals negative I. And that would be how we would address a quadratic equation look like that. Frank?
So what is it called when you move the I behind the number?
When you move the I behind the number?
So 3I.
Oh, we're gonna get there. So are you talking about like 3I or I to the 3rd?
3I.
Good gravy. Not you, Mario, throwing desks. 3I, 3 is just coefficient. So this would be like saying 3 times the square root of negative 1, which we could say like that's the square root of negative 9. Okay, and kind of working in reverse. And one of the skills that you guys will practice will be simplifying out radicals that have negative square roots that have negative radicands. And I'm gonna show you how to pluck out the I. We'll talk about that in just a sec when I show you a gross picture. Oh, there it is actually. There's a naughty movie. I don't recommend it. It's called Kill Bill. And one of the yeah, thank you for whistling. One of the scenes is where Uma Thurman's character named Beatrice. She has a sword fight with a evil assassin woman in a trailer, and she winds up like plucking that woman's eye out. It's disturbing. It's gross, especially when she drops the eyeball down and squishes it with her feet because she's not wearing any shoes. And so, anywho, but what she did there was she plucked out the eye. They were fighting. They had crossed swords, and she just reached up and snatched that eye out. And so that's what you guys are going to do. You're going to snatch the eye out. You're going to pluck out the eye. And what we're going to do is we're going to practice with these 2 examples. Go ahead and jot these 2 examples down. Square root of negative 162, square root of negative 50. Up to this point in your mathy careers, you would have thrown on the brakes and said, I cannot do this. This don't work. But now I'm going to show you how it does work. Now, by the way, I'm missing Finley and Sebastian and Steven. I got to do my attendance real quick. Finley. There's Steve Areno. And smelt. Absolutely safe. Should have done that earlier. Sorry about that. All right. Now the rules, the same rules apply as to how we would work with these square roots of negative numbers as they did with regular square roots. So Stephen, I'll put the burden on you first. Do you see a perfect square that is a factor of 162? All right, so yes, 9 does go into 162. Very nice. 9 goes in 18 times. Okay, 9 times 18, which tells me 18 also has another 9 in it. That boy, good. And do I expect us to get like right there every time, right off the bat? No. And so you could take what Delta Math would call like the slow way, which is like to cull out the 9 and then to realize, oh, I got to take another 9 out. But the quote fast way would be to write it up as such. So check this out. Here we go. We're going to write this up as the square root of 81 times negative 1 times 2. And I put that in a weird order. I did, because I want to show you this is the proper order of how we're going to write things. We always write our coefficient first. Now, what's the square root of 81? And then we write our imaginary number. What's the square root of negative 1? And then we write if there's anything left in jail, we just put at the end right there. Something's happening to my computer. There we go. Okay, so we want coefficient, then I, and then square root if there is any square root left. Mario, and then Eli.
Before I looked at an example, I did take a photo of it, and it put the I like inside the radical is 9 to radical 2 I. Is that different, like acceptable way of doing it, or is that?
So it's going to depend on the context. I gotta warn you, be careful. Okay, because check this out. We'll ignore the I for just a sec. Can y'all see how the second one might present some issues?
Yeah.
Right, Freddie, what's the issue with that second one? I think your eyes must have been closed. This second one. What's maybe hinky about how I written this up?
It looks weird.
All right, so there's a little bit of ambiguity there. It's like, is that square root of 2 times 9, or is that the square root of 29? And so that problem gets exacerbated if we have an I as well. So like if I did 9 square root of 2 I, just be careful. Yes, it's helpful to know what so what photomath is doing is it's saying this is the real part of this term, and this is the imaginary part of this term. We'll discuss kind of what's called A plus BI form here in a little bit, but I caution against it. I typically like to see the radical at the end, and then any imaginary number in the middle, and any coefficient up at the beginning, dictated by the context of the problem that we're working. Eli?
Look up the square root. Immediately turn to I is the thing to be this answer to the next one.
No, please put it as I. Fabulous question. Nicholas?
If I was in the square root, you just take it out. Like if it was negative 162 times I, you just take I out.
No, that's getting a little bit more complicated, having a radical inside a radical. Okay. And that would go back to our Algebra 1 class where we've talked before about square root of the square root, right? So like the square root of 2, you could think about it like this. You could say, well, I'm gonna change color. Let me deal with what's on the inside first. So this becomes the square root of 2. Instead of using 2, let's use something like 7. 7's easier to consider. So this would be like 7 to the 1/2, right? Because of our phrase that pays. Denegri, I think, had helped me with that one time. The phrase that pays is what? Power over root. That's how you would change. So what's in green there, right? What's in green there is just a legit swap out. And then you would say, okay, well, I bet I could do that again. And I could say, well, that's 7 to the 1/2 to the first power under the square root. So we wind up saying, well, that's 7 to the 1/2 to the 1/2. And what's 7 to the 1/2 to the 1/2? 7 to the 1/4. Now, you may or may not remember this from y'all's Algebra 1 preparation, your Algebra 1 class, but there's also a rule in here in red that says if you've got the nth root of the mth root, then that's the same thing as the n times m. All right, so that rule applies there. But to short answer your question there, Nicholas, no, you're not going to have an I inside a radical unless there's some weird circumstance, and that would be covered later on. Good question, though. Do these exponent and radical rules ring a bell? Just kind of jogging some memories a little bit, Fred?
So
Hmm?
if you have like something like root or square root and then like 8 in the middle, that'd be the same as like the
Fourth root of 8. Absolutely. And that's what this rule does. It allows us to bypass all this bull malarkey and just get right down to the end. So like what's 2 times 2? That's 4. So this would be the fourth root of 7. Right? The fourth root of 7. So like you could upsize, you could make it like, hey, I want the cubed root of the square root of x. And so what is that? That's the 6th root of x. You're multiplying, not adding. You're multiplying. And then a power of a root, we would say that's x to the 1/6. Okay, so just some Algebra 1 review, good little recap for us. Let's get back to square root of negative 50. And is everybody cool on how this would be 5i radical 2? Let me show you on your calculators how you could do this. What you want to do is you want to consider what mode your calculator is in. And it's important to always understand the mode your calculator is in because that's how it's going to spit out the answers for you. Let's move this down. All right, so I'm gonna hit the mode button and I want to notice, about down halfway down the page, I'm in A plus BI mode. Now that's the default setting, A plus BI mode. Make sure your calculator is in that mode, okay? Because if it's in real mode, I'll get an error message when I try to take the square root of negative 50. I'll show you what I'm talking about. So there, I'll put it in real mode. And I'll do the square root of negative 50. And it says non-real answer, womp womp. Okay, but what mode I'm in, when I change that mode to A plus BI mode, now I hit square root of negative 50 and I get 7.07i. Right, now what's the problem with that? 7.07-ish. That's an approximate value. That's not an exact value. What did you guys tell me the exact value would be? 5. Now, does anybody know where the I button is? Very nice. Second decimal. So 5i radical 2. I hit enter, and lo and behold, I get the same exact value. So it's sort of like a hack as far as how you could check to simplify. You could check your work on simplifying these. Eli.
wait, what?
A plus B.
Sadly, no. Sadly, no. Somebody, it might have been Kenneth. Were you talking about simplifying radicals and using the table? That was Aiden. Sorry, proximity. I just couldn't remember face. So like Aiden found a way of like getting the calculator to, in sort of a roundabout way, simplify radicals for you. And I would imagine that works in this case. I'm not up to snuff on it, but I imagine it maybe could be done. And then we just plug the I in the middle afterwards. I'm a degree man. I like to keep my calculator in terms of degrees. If your calculator is in radians, that's okay as well. Once we start studying trigonometry, you'll be swapping back and forth. You want me to teach you trigonometry right now?
Oh.
Woo-hoo! Oh, baby, we're doing it.
Bro,
No, like.
Y'all would love taking my trigonometry class. That's what the fourth quarter. All right, so 1 degree is like a teeny tiny little 1/360th of an angle of a rotation. Excuse me. There's 360 degrees in a full rotation. 1 radian is, I think it's like 57 degrees ish. but the radian is the angle at which the radius and the arc length are the same length. And so if you've moved your angle up and up to where the radius carved out the arc length and those two values are equal, that's what 1 radian is. And the way that you convert degrees and radians, there's a real cute little lady in this video that I'll show you guys in the spring that she talks about converting degrees and radians. You multiply by 180 over pi or pi over 180. So like 30 degrees gets converted to pi over 6 radians. It's just a different way of looking. I tell you what it's like. It's like when I went up to Canada one time and I was driving my car, I was driving 80 miles an hour instead of 80 kilometers an hour. And so that was a bit of a problem. They measure speed differently up there. It's just, you're still measuring the same thing. It's just two different ways of doing it. Same thing with radians and degrees. It's an angle measurement. It's like y'all have with temperature. What are your 3 measurements or units for temperature?
Celsius.
Yeah, you know what I'm saying? So they're all measuring temperature, but they just got different units. So long and short of it is I'll leave my calculator in degree mode. That's what I would recommend for you. But we've practiced plucking out the I, simplifying some square roots. Did y'all have some of those questions on your Delta Math? All right.
Those were easy to find. And you just slide an eye on a regular in your eye.
All right, well, 216 then. If it's so easy, what goes into 216? 36/6. Dadgum, Michael, that boy. And so what will we say? 6I radical 6?
Yeah.
All right. 6I radical 6. And they show us just that. It's meant to be an easy endeavor. I hit I on my keyboard.
Keyboard.
It's like copy and pasting.
Are you for real?
Yeah, I was too.
Simplest solution's always the best solution. All right.
Or the other.
Oh, some of the other questions y'all had?
Well, I did.
Powers of I. All right, so like we'll use Sebastian's. He's not here. I would highly recommend just add all of the exponents since the bases are the same. We add the exponents and 20, 30, 53, 74. So I to the 74th. So that's I to the second, which would be -1. Now, how did I get from I to the 74th? My brain went 2 below it to 72, which is a multiple 4. And if 72 is a multiple 4, 73 would be I to the first, 74 would be I to the second. And so we would say -1. And then Delta Math would be like, yippee skippy, good job. 72 being the nearest one. And this kind of goes back to Nash's question. Like we got 72 and 2. Well, the 72 becomes superfluous because it's 1. And then I just got I to the second, which we memorized is -1. I do highly recommend that you commit to memory those first 4 powers of I with a black star rounded up there in the middle of the screen. I, -1, -I, and 1. And that's the pattern that it repeats over and over and over. Sorry. All right. Now for something a little more interesting, I think. All complex numbers have 2 parts. They have a real part and an imaginary part. Just pluck the I out. It's like 7. Square root of -7, you would just say I radical 7. Technically, you can say square root of 7I, but as we mentioned earlier, just cuidado on that kind of thing. So all real numbers, or excuse me, all complex numbers have 2 parts, a real part and an imaginary part. We call this A plus BI. That's actually what that mode was referred to on the calculator. Okay. And so I should be able to express any complex number in A plus BI form. Now go to Mario's example of 35. 35. That was his real number that he came up with earlier. 35 as a complex number would be 35 plus what?
0.
0i. Very good, Mr. Davenport. So it's sort of like all of these numbers that you've known your whole life were actually complex numbers in disguise. Okay, so like any number that you dream up, any real number, you could just put as plus 0i at the end, and now it's written in complex form. And it's a complex number. So I'll give you a couple examples. There's 2 plus 3i, negative 5 minus 1i, there's 1 plus 7i. And because we operate with complex numbers, it's helpful to give them like a little nickname, you know? So my son's legal name is Theodore Charles Morgan. What does he go by? He goes by Teddy. That's his nickname, right? So this number right here, his legal name, if you will, is 2 plus 3i, but that's a mouthful. I'll just call that Z1. Or Z2 for this number, or Z3 for that number. That's sort of like the nickname. That way, what I could do is I could say, hey, Eli, I'd like for you to add Z1 plus Z2. And it's way shorter to write that out. And what we're going to talk about is with addition and subtraction, all you have to do is add the real parts and add the imaginary parts. All right, so like if Z1 is your first number, Z2 is second number, and I say, boys, I'd like to add Z1 plus Z2. We'll just do the real part plus the real part and the imaginary part plus the imaginary part. Okay? It's just that simple. And then similarly with subtraction, you're subtracting the real parts and you're subtracting the imaginary parts. I highly recommend that you write down what's in blue right here under the orange. We're going to be performing operations with complex numbers. First operations are adding and subtracting. Now, much like Mario mentioned, like your photo map apps, your Wolfram Alpha, Mathway, all of these apps will do these for you. And that's because the graphing calculator can do these for you. And in fact, it's super simple. And usually with simple examples, I wouldn't even bother plugging it into the calculator, to be honest with you. But it's nice for you guys to know how that works. So here's what we're going to do. Really would like this stupid tag to get off of here. Yes, I know I'm sharing my screen. All right, so look at example 4 right here. I'll give you 3 complex numbers. Say Z1, Z2, Z3. There we go. Just made up some random examples. We're going to practice adding Z1 plus Z2. So I'll do it the slow way. Okay, so that's going to be 2 plus 3i. That's Z1. Big fat plus sign. And then negative 5 minus 1i. And we want to add the real parts and add the imaginary parts. Henry, add the real parts. What do you get? Very nice. Fredo, add the imaginary parts. What do you get? This and this. What's 3i? Negative 1i. Bingo. And it feels so weird, doesn't it? It feels strange, like, I don't know what I'm doing, Coach Morgan. Well, what we can do is we can treat I like a variable with certain caveats. You know, we're not going to get crazy with it. But as far as like adding and subtracting complex numbers, we just treat it like a variable. You say, well, I've got this many I minus that many I. Okay, that equals 2I. Here's how you do that on your calculator. Literally 2 plus 3i plus negative 5 minus I. And because my calculator is in A plus BI mode, I get negative 3 plus 2i, which is exactly what you guys showed me. Absolutely. So like if I wanted to, let's do 2 plus 3i. I can hit that stow button and I call it whatever I want to. I'll call it A. And then negative 5 minus I could store that as B. And just for kicks and giggles, 1 plus 7i, let's store that for C. So now, what were we asked to do in the first one? A plus B Okay, what do we have to do for the second one? C minus A. You know what I'm saying? And then we could do A minus quantity B plus C. And there you go. There's those three examples done on your calculator using the STO option. Now, I would argue that it took me a lot longer to punch all that in on the calculator than it would have just to do it. In this example, I just gave some rando ones. All right, but like, looky here. Here's how we would do this more at speed. Okay, so I'm gonna say 1 minus 2. What's 1 minus 2? And then we're gonna come back and we're gonna say 7i minus 3i. So that's 4i. And that was the answer that we got for the second bit. And then for the third bit, let's just add our first two numbers. So we got -5 and 1, that's -4. And then, let's see, we're doing 2 plus 3. So -1 and 7i, what is that, 6i? Here's where you have to be careful, though. If I'm subtracting, what do I have to do with that negative sign? D word. I got to distribute it. So if I'm going to do Z1 minus this resulting sum, then I'm going to have to dump the negative in there. Minus negative is going to become plus positive. And so Z1, what's 2 plus 4? That's 6. And 3 minus 6 would be -3. And that would be my answer for the third part. Does that flesh out with what I had on the calculator? 6 minus 3i. Excellent. So adding, subtracting complex numbers, not too shabby. Questions, comments about it? All right. Let's talk about conjugates. Oh, go ahead, Aiden. Yes, hustle back, though, because I don't want you to miss this. Here's where it gets real interesting. I told you that my friend Adam, the youngster that I taught once upon a time that made the pocket people and called them the Z-barians. This is where he got Z-bar. A complex number, if you name it Z, its quote conjugate, the notation for its conjugate is Z with a little line over the top, Z-bar, in other words. Okay, and complex conjugate just means change the sign in the middle. Now, what do you notice in purple there happens when I add a complex number and its conjugate? 2a, describe that number. Classify that number based on our discussion earlier with concentric circles. It is a real number. All right, so when you add a complex number with its conjugate, the result is a real number because the plus minus bi cancels out. If I subtract a complex number minus its conjugate, I get a strictly imaginary number. The real part goes away, and I'm left with just strictly the imaginary part. Okay, so adding and subtracting a complex number times its conjugate, kind of a unique occurrence, but where we really are going to enjoy this notion of using conjugates is through multiplication. Now, what process does it maybe do we maybe think we're going to be using when we multiply a complex number that has two parts and a complex number that has two parts? You got 2 parts times 2 parts. What process does that look like? It's a FOIL problem. And so when we say it's just FOIL, that's very true. A plus bi, C plus di. If I multiply these two together, I get FOIL. But that L has an I squared in it. And what did we say I squared is? Same thing as -1. So what that does is that turns the first, that's your F, and the L, that's your last. The first and the last, the F and the L, come together to make the real part. Okay? This is where I wanted my whiteboard on here. The O and the I, they come together to make the imaginary part. So with complex numbers being multiplied together, it's not FOIL as much as it is flowy. All right, so the F and the L provide us with our real parts. The O and the I provide us with our imaginary parts. And what happens when you're multiplying a complex number times its conjugate is that the OI cancels out and you're just left with what? If the OI cancels out, then you're just left with a real number. So multiplying a complex number times its conjugate does away with the imaginary notion and it turns it into a real number. And we'll see that fleshed out here in a sec. All that's written in orange here, gentlemen, is just a FOIL problem. First, outer, inner, last. And the only added complication is that you've got a couple of terms now, the O and the I, that have an imaginary number as part of it. And so we call them together, we factor out the imaginary number, and that's our imaginary part in A plus BI form. Let's wrap class up by seeing how this would look. This will be our last example. Yeah, so what we're going to do is we're going to multiply 3 minus 7i and negative 2 plus I. And I'm going to go real slow. We'll go real slow with you. Okay. 3 minus 7i, negative 2 plus I. All right, let's go first. Hello, Finley. First times first, it's going to be negative 6. I'm not going to do outer, inner, and then last. I'm going to actually jump to the last. I'm going to jump to the last because the F and the L, you just set it by my water bottle and tuck shirt tail in, and we're recording this class so you can get caught up on what you missed. And then don't forget to turn in your problem set as well if you haven't done that yet. All right, last times last. This is where you got to flex a little brain power. Franklin, you're gonna be my man here. What's negative 7 times positive 1?
Positive 7.
Try again. Negative 7 times positive 1.
Negative 7.
Negative 7. Good. And then what's I times I?
No, square.
I squared is the same thing as
Negative 1.
negative 1. And so you got negative 7 times negative 1.
It's positive.
It's positive 7. Beautiful. Okay. Now, that OI, in just a sec, when we do the outer and the inner, it's going to be a lot easier. I think that the last, the L, is probably the hardest part for folks. So I'll do that again. Franklin helped walk me through that. He did a good job. Just negative 7 times 1 times I. That's negative 7. That's negative 1. And that's why it equaled a positive 7. Does that help illustrate what we're talking about, what Franklin and I just did? Everybody track on that? And then, Nash, you want to do the outer? 3i and the inner? Good. So that sounds like 17i to me. And what I like about the OI is that, man, you could do that. Did we say 17i? Is that what it was? You could do that in your head. So put the F and the L together. What's negative 6 and positive 7? 1. Yeah, we always add. And then the OI was 17i. And there you go. Guess how you could check your work? Calculator. All right, now instead of storing all this stuff, I'm just going to go 3 minus 7i. Close parentheses, open parentheses, negative 2 plus I. We get 1 plus 17i. Isn't that nippy?
So how did the kid get his calculator to simplify radicals for him?
Aiden? You mean?
Yeah, how did he get his calculator to simplify radicals?
Talk to him about it outside of class because he explained it using the table and y equals, and I'll let y'all can figure that out because it went over my head. And I think I also found a YouTube video on it. I just Googled how to simplify radicals on TI-84. And YouTube was helpful there as well. All right, so what operations have we done to kind of wrap class up today? We also did simplifying. So what I'll do is I'll give you guys a little bit of some additional Delta Math work on simplify. Well, you already did simplify. We'll do add and subtract and multiply complex numbers. Okay?
Let me do on Monday.
Yep.
Does it really matter which word you do the?
No, it doesn't. FOIL? Correct. It doesn't matter. I like flowy just because The F and the L come together is the real part. The O and the I come together as the imaginary part. And look, I recognize that this is brand spanking new for almost, if not everybody in here, almost everybody in here. And so it might feel uncomfortable. The way you get more comfortable is with practice. So make sure you put in some practice for me. Please and thank you. And in the meantime, live Jesus in our hearts.
Now,